All right, so you guys can see the unit conversions for length here, and again, just for the purpose of the recording, we're in section 1.5, that we're continuing our discussion with you. So unit conversions, obviously you can see we're kind of using both the standard scale and the metric system, right? Hey, Miguel, I think you are here. Sorry, you're next to Samuel. So foot to inches, right? We should know that. I mean, we live in Colorado. You better know the mile to feet conversion because it's like everywhere. That's how I remember, because I just remember how high the city of Denver is, right? The steps at the Capitol. Thank you. One of those. And then you've got your yard to feet. And then you can kind of see we're getting into the metric system over here, with the exception of course, here you're going between centimeters and inches. So it's approximately, and I kind of hate that they did not use the approximate symbol because it's approximately 2.54 centimeters to an inch. And then of course, we're going between meters, kilometers, centimeters, millimeters. So in these scale, kilometer is going to be the largest measurement. Millimeter is going to be the smallest one. So kind of downgrading in the length, you would have kilometer, meters, centimeter, and then millimeter. And you know, the best thing about the metric system is the words tell you what your conversions are going to be. So when we're talking about millimeters, we're basically saying it's out of 1,000. So you can see 1,000 meters makes up a meter, right? So that's the milli. Centi comes from cent. So that tells you 100. So that's 100 centimeters make up a meter. And then meters is actually the main unit of measurement here. So 1,000 of those meters make up 1 kilometer. So your kilometer would be what you would think about, you know, if you were talking distances between cities, right? Because that's your largest measurement. So think about how we use miles for longer distances. We'd be using kilometers for that. Going into weight or mass. Now the metric system actually weighs the mass. Do we know what's the difference between weight and mass? Yes.
What was it? I don't know. Yeah, it can't be created or destroyed.
Interesting. I have never thought of mass in this context in that way. But that's a very interesting way of looking at it, which kind of builds up to what I'm looking for.
Mass is how much physical space it takes up.
And weight?
Weight is just the weight of the object, how heavy it is.
Well, technically, the mass is also talking
Based
about
on
how
the
heavy
density.
it is, but yeah, mass is like Samuel said, kind of how much space it's taking up. So think about it this way. If we go on the moon, we weigh lighter. Why?
It's gravity.
Less gravity, and that's what weight is. Weight takes gravity into consideration, whereas mass is how much mass you physically have, right? So as far as us going on the moon, it's not like, you know, we lost weight in the flight up there. No, we didn't. Because the gravity is low, you weigh less. And you know, as kids, that used to always be a consolation because my brother and I would compete with everything. So it's like, oh, but I'd weigh less on the moon. So I'm not that heavy, because he'd always like make fun of me. And I was like, yeah, I'm still gonna be lighter on the moon. So, you know, that's a consolation, I guess. I don't know. To a child, that makes sense, right? So just that's the difference between, so kind of like Maddie was saying, you know, it cannot be destroyed, it cannot be created, because whatever mass you have is what the mass you have, right? It's just the weight with the gravity that makes a difference. So conversions here again, a pound is 16 ounces. 1 US ton is 2,000 pounds. And then we're getting into metric again. So you will see the same thing, right? Milli stands for mil, 1,000. So 1,000 milligrams makes 1 gram. 1,000 grams will make 1 kilogram. Honestly, if you can remember one metric system, either meters, grams, or liters, those conversions are all the same. And then going between the metric and the standard system, 1 kilogram, and see, this is what I'm talking about, approximately 2.2 pounds. And you can see pounds is a weight, whereas grams is a mass. So that's why they're saying it's 2.2 pounds in Earth's gravity. Now, if you were to figure out what 1 kilogram is going to be on the moon, it's going to be less than 2.2, right? Because again, same thing, gravity is lower on the moon. All right, liquids, volume and capacity. So we know 1 gallon is 4 quarts. 1 quart is 2 pints, 1 pint is 2 cups. And then from there, we're going to 1 cup is 8 fluid ounces, or 1 cup can also be 16 tablespoons, and 1 tablespoon is 3 teaspoons. Same conversion for the metric system, 1,000 milliliters will make 1 liter. So they're talking about fluid ounces are a capacity measurement for liquid. 1 fluid ounce weighs about 1 ounce for water only. So if you are using a different liquid, the weight will be different because it will depend on the material that you are using. Are we familiar with most of these conversions? Yeah. All right, so let's see how we can use them. So we talk about dimensional analysis usually when we are doing a unit conversion. So the idea is, and we had talked about this when we had talked about rate. So if you know how, if you write the unit of measurements down, you can kind of see which ones will cancel out. So which unit will stay as your final answer. And that's kind of what dimensional analysis also helps us with. So you either use multiplication or division when you're trying to do these conversions. So yeah, basically we will talk about lining up those units to show how the units cancel out and what will stay in your final conversion. So they're talking about, you know, if you are looking at something like 1 pint is 2 cups or 2 cups is 1 pint, basically depending on which conversion you're doing, you can invert that fraction, right? All right, let's look at 1.55. So your dog was stung by a bee and your veterinarian recommended you give them Benadryl. The dosage is 2 milligrams per kilogram of body weight, and you want to double check the dose. Your dog weighs 54 pounds and the tablets are 25 milligrams each. How many tablets should you give your dog? All right. Have any of you worked with dosage before? Yeah? Yeah, I'd imagine you are definitely working. What instance or why did you have to use dosage?
Like, would I have to take like Advil-wise, ibuprofen?
Okay,
Like,
okay, so for personal
yeah,
use.
like medication.
Okay, because you know, that's a big part of nursing, right? When you are training to be a nurse, this is one of the first things they want you to be comfortable about is that dosage, which comes from the dimensional analysis I was talking about. All right, so they're telling us the dosage is 2 milligrams per kilogram, and we basically need to figure out how many tablets should the dog be getting for the sting here. So let's see, our final should be a tablet. So they're telling us 1 tablet is 25 milligrams each. Now you will see I put the tablet on the top because the final question is asking us how many tablets are we going to give this for baby, right? So we need to keep the tablet on the top because that should end up as our final unit of measurement, and that's why I'm keeping it at the top. So each tablet is 25 milligrams. Let's see, the dosage is 2 milligrams. Now, since I put milligrams on the bottom, for my next conversion, I'm going to put milligrams on the top. So that's 2 milligrams. That's the dosage for 1 kilogram of the person or the doggy's body weight, right? And then the dog weighs 54 pounds. Which means we need a conversion to go between pounds and kilograms, yes? All right, and what was that conversion between pounds and kilograms? Roughly 2.2. So since pounds is on the top, we will be saying, okay, roughly 1 kilogram is 2.2 pounds, right, in Earth's gravity. Well, I guess they are. They didn't really tell us they're not. So yeah, we're going to be safe to assume that, right? All righty. So this is the dimensional analysis I am talking about. So we know the final answer needs to be in tablets. We put that on the top. Then they're telling us one tablet is 25 milligrams each. They're telling us the dosage is 2 milligrams to 1 kilogram. So then you flip that, right? The milligram goes on the top, kilograms come on the bottom. The dog itself weighs 54 pounds. So that told us we needed one more conversion between the kilograms and the pounds. Now, since kilograms is on the bottom, you can see I put the kilograms on top. And then with the 54 pounds, since pound was on the top, we of course put the pounds on the bottom in our conversion factor. And then basically what happens is your milligrams, the unit of measurement cancels out. Kilogram. There we go, kilogram cancels out, pounds cancel out, right? Top and bottom, top and bottom. So you will see once we get this whole math completed, it will tell us how many tablets will be needed. So how are you going to do the math here? And if it helps, visually, you can write that 54/1, so you can kind of see it did have a denominator in there. So what do we do to calculate the final answer here? Say that again? Very nice, exactly. So multiply on the numbers on the top, multiply on the numbers on the bottom, and then divide the two values over here. So let's see what do we end up with. We're basically doing 1 times 2 times 54 times 1 on the top, which really is just 2 times 54. Which of course doubles that, so that becomes 108. On the denominator, we've got 2.5 times 1 times 1 times 2.2. Did I say 2.5? Should be 25. 25 times 2.2. And that will give us. All right. And then what is 108 divided by 55? Approximately. Six, so what do you think you're going to give the dog here?
2 tablets.
2 tablets? Yeah? All right, let's check and see if that's what they did. You can see they kind of broke it up into multi-part process, and you can do that. Also, I kind of like having to see the whole thing laid out because it makes more sense to me. But if you're more comfortable taking it step by step, that's definitely an option. And that's the beauty of multiplying and dividing, right? You can do it in different orders, but it's still, I mean, multiply in different orders, not like you change the multiplication to division, but you can multiply different numbers in different order and you're still going to get similar result. So you can kind of see how they broke that down, and then obviously coming up with the same answer, 1.96. So they're kind of talking about here, the acceptable would be 2 tablets as we guess, but liquid forms definitely work out a little bit better because you can be a little bit more precise if it's a liquid medicine, right? So you could probably get down to about 1.9, you know, whatever they were doing, milliliters or whatever, but tablet, you could do 1.5-ish, but not really 1.9. Yeah,
Liquid medicine is way harder to give a dog than tablets.
I agree. Well, depends on the dog. Because I was taking care of this one pup when I was visiting my family in India, and they gave us tablets for him, but I'd rather go fight World War III than give him that tablet. So we did crush it, mix it with water, and then just took a big fat syringe and we're like, open. So
Peanut butter also works.
Yeah, he was not that easy.
My dog hated peanut butter,
Sure does.
despised it.
Really? Yeah, this one, I think he had never eaten peanut butter. So I don't think he knew the taste of peanut butter, which again, you guys should know, Indians are not very big on peanut butter, so.
What?
Yeah, it's
But
not a
it's so good.
staple in India. I did not see peanut butter till my aunt was visiting and she brought this big jar of peanut butter because her son, that's all he ate.
I know what I'm doing.
So,
Flying to India, bringing peanut butter.
okay. Good luck. I mean, I think of other things, but sure, peanut butter works. Alrighty, so that was conversion of units, right, using dimensional analysis. Before we get into the geometry part, let's pick another example here from our. Okay. Sure, why not? Let's look at 19. You are in charge of drinks for a neighborhood block party. You need at least 100 cups of beverages. So far, you have received enough mix to make 3 gallons of lemonade, 6 bottles of fruit juice that each contain 32 fluid ounces. How many cups of beverage do you have so far? Is this enough for the block party? Yes, it is. Very nice. So you got a head start on you. All right, so we know how many total cups of beverage we need, right? So they're telling us we need at least 100 cups of beverage. Do we have 100 cups of beverage? So we have received enough mix to make 3 gallons of lemonade. So of course, we need to convert those 3 gallons to how many ever cups they are going to be, right? And then they're telling us we also have 6 bottles of fruit juice, which is, each bottle contains 32 fluid ounces. All right, let's start with 3 gallons and let's start by converting it into cups. So what conversion are you looking at here for 3 gallons to cups? Do we have a gallon to cup approximation?
Yeah.
I mean, in here.
Oh, yeah, no.
Evil.
That's been done.
Gallon to cup. Well, we gotta go step by step by step in this case. I mean, we could cheat and use Google, but I'm not. So I want cups on the top, and we don't know how many cups it's gonna be, so I'm gonna go to my little friendly neighborhood X for that. So they're telling us we need cups, which means our first conversion would be 2 cups on the bottom, 1 pint. Yes? Well, but do I wanna cancel my cups? No, I don't. I'm doing this wrong. Sorry. Not thinking. I want my cups on the top because we're looking for cups. So 2 cups on the top is 1 pint. And then let's see, since pint was on the bottom, you put it on the top now, and the next conversion is going from 2 pints to 1 quart. And I should have used a better space. Since quart is on the bottom, quart will go on the top in the next conversion, so 4 quarts is 1 gallon, and we had a total of 3 gallons of lemonade? Something, one of those drinks. No, I'm sorry, do we see that conversion? You want me to write it in a bigger, better place? Okay, so the pints will cancel out. The quarts will cancel out. And the gallons will cancel out. So on the top, right now, we have 2 times 2 times 4 times, and again, if it helps, you can put that as 3/1 gallon. So let's see, 2 times 2 times 4 times 3, and all the denominators were ones, right? So we don't really have technically a denominator that we need to worry about. So what is 2 times 2 times 4 times 3? Anybody? Very nice, 48. So we have a total of 48 cups. So about halfway-ish, right? Remember they told us we needed 100 cups of drinks, I guess. All right, so this was coming from just the lemonade. Yeah, so this was lemonade. All right, so now we have 6 bottles of 32 fluid ounces of some kind of juice. So where would you start in this case?
6 times 32. See how many ounces you have?
Very nice. Yes, start by finding out ounces. So what is 6 times 32?
92.
192, 18, and 12. All right, so fluid ounces, right? Which means we still need to convert this guy into cups, and I think
8.
8, yeah. There you go. So this one will be a simpler conversion, so you are looking at cups again, and so let's see, we wanna keep cups on the top, so 1 cup is 8 fluid ounces, and then multiply that by 192 fluid ounces, which you will see in this case, we end up dividing, right? So what is 192 divided by 8? 24. Perfect. Do we have 100 cups of beverages? How many total beverage cups do we have between the lemonade and the fruit juice?
72.
Yeah, 48, 52, 72. Yeah, so basically at this point, we would be adding our 48 cups from the lemonade, 24 cups from juice. We are actually not gonna have enough for everybody. Water bottle. Right? So obviously you can see we are going to be shy of at least the basic requirements over here. So just your basic conversions, you can see the gallons was the one that took us, multiple conversions to get there. But as I said, you can actually just come up with a direct conversion between gallons and cups through that math, or just like I said, Google can help you in that. Or go through the process we did over here. And then of course, for the other one, you had to first take how many total juice quantity did we have? So that was 6 bottles times 32, and then add the 2 quantities together. Anybody have questions on this guy here? Okay. Now we can look at some of those geometric formulas. So some of the basic ones over here, of course, we have rectangle, where we know one side is longer than the other. So we have your length and width. So the perimeter for a rectangle is you take 2 of these lengths and add it with 2 of the width, right? So 2 times L plus 2 times W. The area is going to be length times width. Circle, of course, we call the perimeter as a circumference. So that is 2 pi r. And then the area is going to be pi r squared. Now you should notice that for perimeter, you have a single unit of measurement, right? So it's just going to be centimeters or inches or feet. But when we talk about area, it's square units. It's going to be square centimeter, square feet, whatever might be the case, because you're multiplying 2 units here. So you're basically, end up doing feet times feet. And you can see that's where the square feet comes from when we're talking about area. Does anybody know what the perimeter and area for a square is? It is so surprising to me that they didn't include that. What's the perimeter for a square?
Wouldn't you find it the same way you find the rectangle?
Very good. Yeah. So what do you think, It should translate as, because what's the difference between a square and a rectangle?
Equal sides.
All four sides are of equal length, yeah. So if we were to do that using the perimeter for rectangle formula, what do you think it might end up looking like for a square? Well, if you did 2 times the side plus 2 times the side, just replace the length and width, right, with side and side. What would that come out to? 2s plus 2s. 4. So basically, the perimeter of a square is 4 times the side. Since all 4 sides are the same measurement, you can do s plus s plus s plus s, or you just do 4 times the s. What would be the area of a square?
Would it just be side squared?
Very nice, yes, it is going to be side squared. And then, of course, since it's an area, it's also going to be in terms of unit square. Okay. All right, so that was perimeter and area, and of course, we'll come and look at examples for that. Volume, again, we're going with a rectangular box. Now, technically, this formula would also work if you're looking at a cube, if all sides were the same measurement, right? But again, if it's a rectangular box where the 3 lengths are going to be different, you are basically taking length times height times width. Yeah, I just changed the order. Length times height times width, and this is 3 measurements, right? So you're doing feet times feet times feet. So it's going to be a cubic unit, which makes sense, right? Because we talk about a cube, so we know it's going to be a cubic unit. This is, of course, you can see a cylinder with a circular base. So since this is a circular base, what you are actually doing here is taking the area of the circle. So taking the area of the circle, which you will see is pi r square, and that's where that pi r square is coming from, and then basically multiplying it by the height of the cylinder. So that's where the h is coming from. So pi r square h becomes the volume of cylinder. How do you think, and this is critical thinking, how would that change if you were to change the circle to a different shape? How would your formula change? What if we changed it to, like, you know, a triangle instead of a circle?
You would be using pi.
Okay, what else? Because we use the area of a circle, right? Because we had a circular base on our cylinder. So if you have a triangle as a base, which would basically be a prism, instead of the pi r square, you would use the area of a triangle, right? Which is 1/2 base times height. So you just actually, because the height will always be there, it's just whatever shape your bottom is going to be, right? Which is what the area is, and then times the height. That's kind of how you can switch that if you're changing shapes. All right, let's look at a couple examples here, and then we'll pick one from the bottom. You need to replace the boards on your deck, and you'd like to do it yourself to save money. You want to estimate how much you will need to save up for the wood. So you're kind of estimating here, where would you start if you want to change the boards on the deck?
Mention the deck.
Any numbers, okay? Square footage of the deck, then where would you begin?
By price per sheet of wood, whatever you're using. Material cost.
Ah. Okay. So first we need the area of the deck. What did you say after that?
Then you multiply the area of the deck versus the price of materials that you'll need.
But wouldn't you need to first decide what size board you're gonna use based on your area or how many of them you need,
I guess,
right?
but you could base that off price.
I guess you could, because you can kind of see if this is a more better buy? Would you go with a different shape or size? If that would be more economical, especially since they did tell us they're doing this to save money. So yeah, you can look at the size and price of the boards. What else? This would be the same if you were doing flooring or anything like that, right? Would you have any other expenses on top of the boards?
Sales.
Mhm. Support equipment, right? If you have stuff at home, that's different, but if you need to purchase, nail gun, I don't know, hammer. I have never done this, as you can tell.
You can rent them from.
You can do that, which would be an additional cost, but then again, you can see, do you buy your own or do you rent it out? And yes, renting would be more expensive. But renting makes sense if this is a one and done, right? You're never gonna be doing another house project, never gonna be fixing anything. Then you can say, why should I purchase something that I'm using for one time, right? All right, let's look at the breakdown your textbook is giving. And they do get into some details over here. So the one thing that they said was the estimates usually add 10% for parts of boards that don't get used, so they're gonna put that in there. We need to know the size and shape of the deck, so we were talking about the area. The type of boards and the cost per board, so like you mentioned, do we go with bigger boards? Do we go with smaller boards? Which one is gonna be more economical, more cheaper? Measure the deck, and it comes out to be 16 by 24 foot. Looking up prices, you find 5/4 of an inch by 4 inch by 8 foot is giving you a price of $11.99 each. So that estimate comes out to be, they're saying, can basically come anywhere from $1,000 to $3,000. I like step 3 over here because they talk about, you can literally just go out of the deck and count how many boards are there, right? You can actually measure the boards you have and see, okay, this is what the original setup was. Do I want to keep that same thing? And then you can kind of base it off of that also, right? So you can count the boards, calculate the number of boards, calculate the area, and then the approximate cost per square foot. And these will be in area terms, right? Because you are covering a surface. It's not just a single strip. It's actually going to be covering a surface. So yeah, you are talking about area. Option 3 is they're saying, okay, take the length and width of your deck, multiply it, you get the area, and then you can see we're going into the size of the board. So this one was, the width of the board is 4 inches, so we convert that into feet, and that's giving you approximately 2.667 square feet. Taking that with the price of the board itself at $11.99, you can see what per square foot price comes out to be, and then they're kind of talking about the for the whole deck, you can see that kind of comes out to be about 1,700, and then adding that 10% brings it up to approximately, well, more closer to 1,900, right? So they were kind of saying you can estimate between 1,000 and 3,000, so it looks like you'll have about 1,900 as a cost price in there. And then they kind of go through some other calculations for option 2, so you can kind of see that in there as well. Now, of course, this would work out better if, we had a board size, and then you can kind of calculate, but I think it gives you a good idea of how to estimate the cost. Remember, and that's kind of what we had talked about last week, is if you can kind of estimate what your number is going to be, it at least gives you a ballpark figure. And I don't know if you guys do that, or maybe you may be a little bit on the younger side, so don't want to make any assumptions here, but when you go like shopping for clothes or even grocery or anything, do you kind of see, okay, this is kind of, approximately how many items I've purchased, this was the price on the little tag on the shelf, so kind of how much am I spending? So it's not like you go to the checkout counter and you're like, oh, I spent $200 in groceries this week. Where did that come from? Right? And it does happen to me because sometimes I'm just so tired. I'm like, I don't care. I know I need this. I'm running out of this. This looks good. This is fresh. throw in the basket. I get to the checkout and she's like, oh, $150. And I'm like, what? So, so yeah, some people will estimate, and my mom was really good at that. Like she had the brain, she was not a mathematician, but her mental math was like so far ahead. Like my dad was even better than her. So their mental math was so good. Like she could tell you close to within a few dollars how much the grocery is gonna cost because she had been keeping track of all those. So I'm not very good at it. Trying to get better at it, right? So you can kind of estimate, this is kind of the ballpark figure I'm going to be in. All right, second example here is talking about you are making many pizzas for a large party. Your favorite recipe makes 20 ounces of dough for two 12-inch diameter pizzas. You want the pizzas to be larger for the party, so you plan to make completely reversed that, didn't I? 16-inch pizzas. So how much dough do you need, and by what factor should you multiply or scale the recipe? That is a lot of pizza, but they did tell us it's a large party. So they're telling us normally the recipe gives you 20 ounces of dough, which will give us two 12-inch diameter pizzas. This person wants to make six 16-inch pizzas. So we're increasing the size of the pizza, right? We're going from 12 inches to 16 inches, and then we want to make 6 of them. So how are we going to scale up this recipe? We are in a hole here, people. So take a minute, think about it. How are you going to scale up the recipe? Do you see those, I don't know if you'd call them memes or quizzes or stuff on social media where they're like, oh, this restaurant gave you two 6-inch pizzas, but then they were like, oh, what if I give you like a 12-inch pizza, single one, and it's gonna be the same as two 6-inch pizzas, and then you get into the area of the circle and you realize, oh, actually that wasn't the same. So pizza is a circle, yes? We're talking about a diameter. Yes, for our purposes, it's a circle, unless I'm cooking and then it's whatever shape of the state it needs to be today, right? But let's go with circles. And then we're trying to figure out, okay, if we're changing that diameter from 12 to 16 inches, how much more area are we looking at? And you did see the formula for the area of a circle up there, which was pi r squared. Now they are giving you a diameter. How would we change that diameter into a radius for a circle? Yeah, very nice. So when we are talking about a diameter, that's the full length, right, of the pizza. And when we're talking about the radius, it just goes from the center to the edge of the circle. So basically two radii make a diameter, right? So 12-inch diameter comes out to be a 6-inch radius. 16-inch diameter will be how many inches for a radius? Yeah, very nice, 8. Take half of that. Alrighty, so let's find the area between the two pizzas. So you've got pi. R is 6 for the smaller one for the original recipe. And then for the party size, he wants to go or she wants to go, I guess they didn't really tell us. 16 inches, so 8-inch radius. So what area are we looking at between the two sizes of the pizza, the 12-inch pizza and the 16-inch pizza? Six. Okay. Okay, so we can see the difference between the area for the two size pizzas, right? Okay, so the original recipe gives us 2 of the 12-inch. And we want to make 6 of the larger size. So what are we looking at in terms of those new areas? You're gonna take this number, multiply it by 2. We'll copy paste here. No. No, that's supposed not to be. Yes. Always. Oh. All right, so that's the total area for the 12-inch, which is the original recipe of the dough. And this is the area we need if we're gonna go from 12 inches to 16 inches times 6. Okay, so how do we scale up? What kind of math do we need to do so that we can change that recipe from giving us 226.19 to approximately 1206.37? Did they say ounces or ounce? Ounces? It's ounces, yeah. Oh, but was it say pounds? You're feeding an army. Ounces, yeah. Or we're feeding boys.
An Italian in that one.
What do you mean? All right, so how do we?
Italian.
Okay, sorry, I guess you can say that for your own people.
We have eaten pounds worth of pizza before.
Yeah?
Yeah.
Right. Your pizza's good, it's delicious. So how do we go up, you people? Come on. What do we do?
Multiply?
Do we multiply?
I'm throwing shots.
You kinda, Anna, you look like you're thinking. The 226 with 1206?
No, I guess it'd be divided by.
Because we wanna know how many times more pizza, whatever we're going to need. So yes, you are going to take the 1206 and divide it by the original area. 5.33333, right? So that means we are going to need, what was that, 20 ounces for the original? You are going to need approximately 107 ounces of pizza dough. So you have to increase that recipe by 5 1/3, right? 5.33333, that repeating 3 is going to be your 5 1/3 times. All right, let's see if we will get that correctly or not. Oh, they actually changed it to pounds. Their math is a little bit different. And you guys can go see that on your own, but you can kind of see.
Ounces again.
We did come up with the same ratio, right? 5 1/3. But they just did it. I don't know why they went to pounds. And then came back to ounces. And then they're rounding that to 5.34, which we had the 5.33333. All righty. Scaling of a recipe. Let's see if we can find some. I like the example that Samuel sent.
Right, such a 2.
Yeah, this is the one I was talking about. Yes, you did send me to.
That was a dump.
It's not. Do not listen to him. It was not dumb.
Right.
Aminata? Am I butchering that?
Just A.
Okay. Ordered 38 shirts that cost $5 each. She can sell each shirt for $18. What? For $18 and, I mean, yeah. Double I can understand, but this is more than 3 times. Oh my goodness, they better be nice shirts.
Business.
They're not nice shirts if they're $5 each. That's
It's all about
awful.
how you sell
She can sell them for $18 a shirt and ends up selling 31 out of those 38, right? So then they're telling us she returns 7 shirts and pays $2 charge for the return shirts. We want to know how much profit A made. All right, you want to walk me down the math here, people?
38 times 5.
All right, so we started out by purchase, so this is her costing. 38 shirts times $5 a shirt. And what is that gonna be? 190? Okay, now we are selling, the selling price is $18 and she sold 31 of those, so that's 31 times 18, what is that?
558.
What?
I might be wrong. That was that.
I mean, at $18, you know that's gonna be some solid sale that's being made here. Alrighty, and then they are also telling us, oops.
How many shirts did you need to return? 7?
She is returning 7 shirts and having to pay a $2 charge, which is 14. All right. I mean, at $18 a shirt, yes. Whatever she did was very smart. So I want you to tell me what is her final profit going to be? Yes. I love how you like give me an answer, but you're like, oh, I don't know if this is actually gonna work, so I'm just gonna put I think, or maybe.
If I'm wrong, it's not my fault. I can't be held accountable.
Tell me that number again. That's wrong. And there's a reason why that's wrong, because and the reason I picked this because Samuel actually had the same kind of thinking. And I wanted to point out why that doesn't work, but before I get to that part, yes. You said 354, Raven? And you said 480?
That's if she's not paying. Or getting the $5, or paying $5, just the 2 back or return. Or she playing with the rule. She's losing the 5. That's where the conclusion by
5's already gone.
5's just gonna be so the 2.
Still not seeing how you did. We got 558 minus the 190. Not that number. No. You're thinking I'm kind of seeing, but I'm not seeing the math, how you came up with the 480.
Took away the 5,
Do it for that.
because that's not
Double
profit.
sided paper.
So what she invested, I took away.
So shouldn't that be 558 minus 190?
Minus.
Which is how the 354 came about.
Yeah, so you find them. So.
So they're like not accounting for taxes or something?
Yeah, I
Yes.
mean, we're kind of leaving the nitty gritty
Minus the 190.
minus the 190. Okay. Anybody else have a different number than the 2 we have up on the board? How many of you came up with 354? Okay, sorry to say that is incorrect. All right, so here's how it works. And this was my big spiel explanation to Samuel, which I guess you don't have to read it now.
Great.
All right, so we know her revenue that she brought in from selling on these shirts is $558. We also know she had to purchase the t-shirt, so she paid $190. And what was that math? Thank you. So now the question comes out to be, what is happening with those returns that she is making? So here's what you have to think about. Those 7 shirts that she is returning, sorry?
No.
That's what you need to think about. So 7 shirts, she has already paid $5. Somebody said 3.
So the 5, but the 2, so $3 back.
Very nice. She has already paid $5. The company is saying, since you're returning this, we're gonna keep the $2 out of that 5, but the 3 comes back to her. So you're actually taking 7 times 3 and adding it back into this total of $368. So
It's a
it's,
return, not a refund.
oh, but the company's gonna return her the $3.
Yeah, that's fine.
Not if they're charging her.
Have you never gotten a refund?
I don't return things. I buy the thing I need and then I never have to return it.
That makes sense.
That's what I also be known as a restocking fee.
Basically, that's what that $2 is, yes.
That would have been nice if they said something like that.
Yeah, which would be a more, official term in a way, right? The correct term. So yeah, basically the $2 they're keeping and they're giving her back the $3 from the original 5, because it kind of makes a bad business decision. I gave you your merchandise back, but you keep my money. Plus I have to pay you $2 as a return fee. I mean, she did have a really good profit from those $18 a shirt, but the 3 is coming back and that's what you're adding back.
Wouldn't she get in trouble for selling them again?
So,
Oh, but she's returning them, so
To
she
be
won't have
fair,
them.
She's not even giving. them
there are
back.
businesses that run like this, where they will sell you a certain amount of product for you to go sell. And then at the end of your cycle, if you don't sell it, you have to sell that product back to them and they don't give you any of your original money back, which incentivizes you to sell more.
That sounds like a pyramid scheme.
It is a pyramid scheme. You ever heard of doTERRA? Oh my goodness. Essential oils, that's how they sell them.
Well, apparently, I did the teacher preview, so it's not letting me submit my answer. My apologies, guys.
Well.
But you know, we got the same answer.
We're gonna still get through some more.
I strangle him. I don't know.
Go for it.
Hold that one. Other than Samuel, are you guys understanding the process here? Yes, are we good on this question? Yes, all righty. All right, so your textbook kind of does this weirdly. So apparently in the state of Oregon, that's all they need for their logics and problem solving and set analogy. We will be going down 2 more sections into this. So they kind of did 1.6 as a review. And then we go, so we're kind of skipping 1.6 because we don't need a review at this point. So we're actually going into 1.7. So that's why you will see in your homework, we will be jumping from section 1.5 directly to section 1.7 to keep up with the numbering of the textbook, but we didn't officially skip 1.6. 1.6 is just what they're calling chapter review. Okay, alrighty guys, so let's get into. So we're actually going back to logic that we talked about right at the beginning, and we're building up on that by using truth tables. So if you'll remember, we had talked about like the negation of statements by using like not in the statement. We had talked about taking 2 propositions and connecting them together using the word and or the word or. So we had the and or the or statements, and then we had also looked at the conditional statements, the if then, and we had looked at biconditional statements, if and only if. So we're kind of building up on that, but like I said, we're doing this with truth tables. So you can see they're saying this is an extension of the logic, that we did in the first section. All right, so let's take a look here. So in logic, we use the truth table to basically take what could be potentially a complex statement. So, if there's two parts coming together by using the word and, using the word or is it set up as an if-then statement, or is it set up as if and only if? But we need to break down, okay, what if one statement is true, but the other one is false, or both of them are true, or both of them are false? How is that going to affect the validity of the statement? When is it going to be true? When is it going to be false? Now, instead of, kind of breaking it down into making sense in terms of English and then trying to see, the truth table symbolizes it, right? And then makes it easier for us to break it down and say, okay, if this and this happens, then the statement is valid. If this and this happens, the statement is not valid. So here we're talking about analyzing a complex statement by summarizing all the possibilities and their truth values, which is of course true or false. To do this, we break the statement down to its smallest elements, the propositions, and then the outcome will be based on the possible combinations. So here they're talking about statement R or proposition R. You paid your rent this month. Sorry?
I certainly hope so.
Yes, definitely. And proposition E, you paid your electric bill this month, right? So the R is representing the rent, E is representing the electric bill. So based on these two propositions, we're going to try and do it with the negation, the and, which is the conjunction, and the or, which is the disjunction. So I'm seeing some of you are on your cell phones. You do need to put that away. If you're using that as a calculator, I'd rather prefer if you used a standard calculator, because again, you won't be allowed to use a cell phone on the exam, so I don't want you to get used to those. So just please make sure you either bring a handheld calculator or get on Desmos if you need to, okay? All right, to set up our truth table, you actually start with the two individual propositions. So you can see how we're setting it up in that table on the right-hand side. You have the proposition R, the proposition E, and then we're using and to combine them, right? So we're basically saying you paid your rent this month and you paid your electric bill this month. And then you actually list all the possible truth value combinations. So if you have two initial propositions, this is always going to be your setup, where you start by setting, whoa, I forget that. You start by setting both of them as being true. Then the first one is true, the second one is false. The first one is false, the second one is true, and then both statements are false. Now, these may seem similar, but they're not, right? Oh my God, sorry. Let's just do it. Because in this one, we're actually saying R is true, but E is false, right? And then the second one says R is false and E is true. So you're actually changing the truth value between those. So you're not going to get the same results, and it will depend on, are you working with conjunction, which is the and? Are you working with disjunction, which is the or? Are you working with negation, the not? If then, or the if and only if. So based on that, these values will change. Okay, and I think that's kind of what they're going to, that little paragraph. All right, so here are the four cases. You have basically paid both your rent and your electric bill, so both are true. You have paid your rent, but not the electric bill, so T for R, F for E. You have not paid the rent, but you have paid the bill, so that's a third statement. R is false, but E is true. And then, of course, we haven't paid either one of them, neither the rent nor the electric bill, so that's both of them are false. So this is how the truth tables look like based on which complex statement you have here. Okay, so when we're talking about negation, that basically means we're saying, I paid the rent, I did not pay the rent, right? So if the original is true, then your negation is going to be the opposite truth value. So if the original is true, the negation is going to be false. If the original is false, the negation is going to be true. So you can see this is what happens with the negation. So the truth value is going to be the opposite for the negation. When we're talking about and remember, this is where we had used this symbol for and. So this one we are saying if both the values are true, that is the only time a conjunction statement is going to be true. And we did talk about this, if you kind of go back and look at your section 1.1, we had talked about both parts have to be true for an and statement to be true. So if any one of them are false, and you can see that in the second, third, and the fourth row, if even one of those values is false, your combined and statement is also going to be false. So if you can just remember that the only time this statement is true is when both individual propositions are true. With the or, remember we said it can be one or the other or both. And you will see that happen in the truth table over here. So remember the symbol for or is the upside down of the and symbol. Kind of looks like a V. So in this case, we're saying you paid the rent and you paid the electric bill. So both are true. Your or statement is true. You've paid the rent, you did not pay the electric bill, but one of them is true. So the combined statement is true. Reverse that, you didn't pay the rent, but you paid the electric bill. So again, one of those is true. Your or statement is going to be true. The only time the disjunction or the or statement fails is when both of them are false. But in every other case, it's going to be true. And that's this meaning of inclusive ors, right? It's one or the other or both. So you can kind of see that here. It's one or the other or both. So that's how it translates into a truth table. Let's get rid of that. They're having us do conditional, and then we'll come and look at some examples for this. So this is the if-then statement. When we're talking about conditional, and remember this is where you use the arrow, and I'm just gonna use R and E for now, but the symbol wise, it would look like, going from, those names are not coming to my mind. The premise and the conclusion, right? That's how you set it up. So to understand for the truth tables for a conditional statement, we need to look at the context. So here they're saying, okay, if you post that photo to social media, you'll lose your job. And we had seen the same statement in section 1 also. So if you post that photo to social media, you'll lose your job. So we're basically saying under what conditions can you say that your friend was wrong? So here are the 4 possible outcomes. You post the photo, you lose your job. You post the photo, don't lose your job. You don't post the photo and still end up losing your job. And you don't post the photo, you don't lose your job, right? So you can see how they kind of go about talking about that. So the only case where you say your friend was wrong is the second one, because you did post the photo, but that did not affect you, right? You did not end up losing your job. So, yeah, so you posted the photo, but you still kept to keep your job, which is where we would say the friend was wrong. Your friend did not say anything about what would happen if you did not post the photo. So the last 2 statements technically cannot be wrong because they did not say what would happen if you didn't. They never said if you don't post the photo, you will get to keep your job. So even if you didn't post the photo and lost your job, your friend never said that you were guaranteed to keep the job if you did not post that photograph. And I know that kind of seems a little bit of a gray area, but again, we're not dealing with these as consequences, right? We're just thinking about this statement that is presented to us. Is that correct or incorrect, or is it valid or invalid? Not even so much as correct or incorrect, but is it valid or not? Is it right or wrong in terms of its value? So the 4 cases that we listed above kind of look like this in a truth table. So you posted the photo, right? So that's true. You lost your job. That's true. So we can say, okay, the statement is true. You did what you were asked not to do and you dealt with the consequence, right? So that is true. The second case is the one where we said your friend is wrong because we said the photo was posted, but you still get to keep your job. So that's the only time you will see a conditional statement being false. So the first part is true, but the second part is false. Now look at the other two cases. You did not post the photo, but you still ended up losing your job. And this is what we were saying. Your friend did not mention, if you didn't post the photo, you'd be safe. There was no mention of that. So there's no part of that statement. So even though you did not post the photo, you ended up losing your job. Or you did not post the photo and you did not lose your job. So technically the statement was still valid because you didn't do the deed, you didn't have to deal with the consequences, right? So again, that makes the statement true. So honestly, the only place you really need to be thinking about is when the first argument is true or proposition is true, the second one is false. That's the only time a conditional statement fails. So the first one is true, second one is false, and this is where the statement fails. So this guy is the only one that kind of stands out as the false. Everything else is going to be true. And then for the if and only if, which is the biconditional. And in symbolism, it's the double-headed arrow. So with this guy, we have A, B. And we call it double implication because it's going in both directions. With conditional, we call, just one direction, so it's just an implication, but here it's double. So you would again have true for both. True on the first one, false on the second one, false on the first one, true on the second one, and then false and false. So the only two places where this guy is true is when they share the same truth value. Otherwise, it's going to be false. So that's what a truth table for biconditional look like. And that is something I would keep handy also once you keep these tables handy. So I will save this image so you guys can see that in your notes, but if you need to make a note of it on your own, and please do that as well. All right, let's break this down. How would we use these rules for our examples here? So here they're talking about creating a truth table for the statement A or not B. So take a look at how we set this up. So your basic setup, we always start with the individual proposition. So you've got your A and B column. Now this one is saying A or not B. This is not just straight A or B, right? So this is saying A or the negation on B. So you do need to start out with the original A and B, but then since you have that negation on the B, you would say, okay, I need to bring in another column for the negation. And then your last column would be where you put everything together. So you can see we always start out with these 4 cases because you only have 2 propositions to begin with. So you're going to have 4 cases. But then you will see in the next column, we are doing a negation. So all of these values change, right? True becomes false, false becomes true. Now, once you have that negation column taken care of, then for the final statement that they were asking us to create the truth table for, you are now only looking at column A and column negation of B. So this guy is gone now. You don't need to look at him anymore. Right? And since this is an or, what did we say about or? As long as one of them is true, your final statement is going to be true. If they are both false, that's when an or disjunction is going to be false. So you will see one of these guys is true, your complex statement is true. Or actually both of them are true, so this guy is going to be true. Both of them are false. This is the only case where it fails. And then again, one of them was true, so you have a true statement in there. And we'll bring sentences and stuff in later. Right now, we just want you to get comfortable with the idea of working with these symbols, the truth table setup. So basically, you can see we have to do 2 steps here. Create a negation column, and then do the or, the disjunction creation of the final statement here. Okay, let's take a look here. All right, so this guy is getting a little bit more detailed. We are actually going into three propositions now. So you will see we have A, B, and C. So when there's only two propositions, we had 4 rows in our table. When you have 3 propositions, you are going to have 8 rows. And the math behind that is 2 to the nth power, and the n represents how many propositions you have. So if you only have 2 propositions like A or B, that's 2 squared, that becomes 4. If you have 3 propositions like A, B, C, that is 2 to the 3rd power, so that's 2 times 2 is 4, 4 times 2 is 8, right? So that's how the math works on how many rows. So imagine if n was equal to 4, you are doing 2 to the 4th power. How much is that going to be? How many rows? 2 times 2 times 2 times 2. Well, we already made it to 2 to the 3rd power, so multiply another 2 to that, which is how many? But yeah, you're gonna have 16 rows. So that tells you the number of rows you are going to have based on how many propositions you have in there. Okay? Sorry? Fun. Yeah, I mean, it is kind of neat that there's a pattern to it. Okay, so I want you to look at the basic setup when you're working with 3 propositions now. We still start with all 3 of them being true, and you're going to end with all 3 of them being false. But here's how I break these down, because I find it easier to look at them individually. So you will see on the very first column, you have 4 truths and 4 falses, right? So 4 T's, 4 F's. When you move to the next one, it's going to be in pairs of 2. So 2 truths, 2 false, 2 truth, 2 false, right? So 2 and 2, 2 and 2 grouping. And then the very last common column alternates. So TF, 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 TF. So start with 4 and 4, then go into 2s and 2s, and then 1 and 1, right? Alternating your symbols. And that's the easiest way I have found to remember, because when I try to do it horizontally, there's too many changes happening. But when I look at it vertically, it makes it easier for me. So that's how I remember these. Okay, so let's break this down. Remember, please excuse my dear Aunt Sally, we're kind of using the same concept here. So you want to start with the parentheses part first. So we're going to do B or C first, and you can see that's our column here. So B or C, as long as one of them is true, and you're only looking at these 2 columns since we're only interested in B and C. So looking at B and C, if one of them is true, it's going to be true. If both of them are false, it's going to be false. So you can see these guys will come out to be 2. Sorry, that should be true and false. Okay. Then you can see there's a negation on the not B or C parentheses. So that means now you are looking at the B or C column and doing a negation on that. So negation, of course, means the opposite truth value. So all the T's will become F's, all the F's will become T's. And the very last thing is now we're going to do this column with A, because you can see now we're saying and A over here. So we can ignore all of these. We don't need those guys anymore. We're only literally looking at column A, and then the last one we just created. And this is and. Remember, and is true only when both of them are true. Otherwise, all of them are going to be false. So you can see this guy is true and false, so he's going to be a false. True and false. True and false. True and true. So this guy's going to be a truth value here. False. False. False, false. As long as one of them is false, I'm not even looking at the other guy because it's going to fail. We know that. So the only situation where this complex statement is going to be true I'm actually gonna go ahead and, didn't mean to do that. Didn't mean to do that either. Alrighty. The only situation where this statement is going to be true is when proposition A is true, but proposition B and C are false. Because you can see in all the other cases, it ends up failing. Only one condition satisfies to make the entire statement true, whatever that complex statement. And we'll start looking at them with sentences and, kind of associating them with words, but right now we're just doing the generic breakdown. And you can see that's how this guy translates here. I'm trying to superimpose it so you can see we match the same truth values that these guys had here, here, and then here, and you can see there's only one case where this ends up even becoming true. Put this in the statement, yeah, look at that. So they're basically saying, what if statement A represents Anaheim wins, Baltimore wins, Cleveland wins? So we're saying the only place where this scenario will be true or it will work is when Anaheim wins, but Boston, didn't they say Baltimore up there? Anyway, either of those cities, the idea is Anaheim has to win, but Baltimore, Boston, whatever they're calling it, and Cleveland shouldn't win, right? Because it was true, false, false. That's the only situation in where they're basically saying this is the only situation where Anaheim will make the playoffs, right? Baltimore does not win, Cleveland does not win, Anaheim. So that's kind of how they're putting it all together. So there's another example here that you can kind of see in a similar way, but they're using the if-then statement in there. So let's break this down. You have got if M and not P, then R. So we of course have M, P, and R as our three conditional or three propositions. So same setup, 4 T's, 4 F's, and then alternating in pairs of 2's, and then alternating as single values, right? Okay, so breaking this down, you actually do want to start with the not P first. So looking at the P column, you would do the not P. Then you are going to do between M and not P, right? So this is where the conjunction will come into play. So then you are going to do between the column M and the not P column. Then you would only be looking at these two for the next one. You will see they brought the R back to the forward because, instead of working backwards, because you are doing the if-then statement. So we're basically saying if blah, 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 then R. So it actually does help if you have that direction as you would write the statement in English. So it makes sense to bring the R value back in the forefront. You're not having to look backwards. You're looking, how you write it out. So we bring the R column back to the front. And then the final, you would be looking at M and not P as my premise, and then the R as my conclusion. And then based on whatever truth values here, we can come up with this column. So let's take a look at this breakdown here. So when we're talking about not P, take the P column and you would reverse all those truth values. So these are pairs, right? T and T, F and F, T and T, F and F. So you can see that alternates. because we're doing the not P part first. Then you are doing an and. So now we are saying M and not P. So you would be looking at the M column and the not P column. And again, remember, this is and, the conjunction. So both values have to be true. Otherwise, everything else is false. And you will see that only happens in 2 of these cases where both values are true. Everything else is false, right? So only 2 cases where that works. We bring the R column back up to the front. And now you are going in this direction from M not P with the R. So this is the direction you're going. And remember what we said here, if both of them are true, it's true. If first is true, second is false, this is where this guy fails. Second is false, first is false, second is true, it's still true. And if both of them are false, it's still going to be true. So the only time this guy fails is right here. Because the first one was true, the second one was false. Now, this is what I'm trying to emphasize over here. Think about it. If we did not have this column here, but we know the direction is M and not P is going towards R, which means you would have to look backwards. So you would have to think, what happened? Okay, you would have to think, I'm going in this direction. And you're having to look backwards. Oh, I'm not even on the right one. No, because you would be going this way. You'd be like F with T, F with F, E with T, E with F, right? So it just helps to bring that R back again to the front and then go in the proper left to right direction. Come up with your table values. Alrighty, go take a break. We'll come back and do at least one example so you guys can get some hands-on practice. So take about, it's 11:11. Let's do a couple minutes break and then we'll come back. And in the meantime, I'm gonna pick an example to get you guys working on this. It will make more sense. All right, let's start by converting letters to symbols. Example 3. Translate each statement from English sentences into symbolic notation. A will represent, I will protest. B will represent, there is injustice. So A, I will protest. B, there is injustice. So how will we rewrite in symbols? Part A, there is injustice and I will protest. Maybe you want to put that away? I gave you a break.
No, but I didn't get time to finish what I was typing.
How will you write this in symbols? If A represents I will protest, B represents there is injustice, we would replace those in the sentence with A and B. Right? So how will you write part A out? There is injustice and I will protest.
You're writing down like the true false or just like the A, B?
Just the words into symbols right now. We're not doing the truth tables. Because you need to be able to do this before you can get into the truth table.
Be like the A and the caret symbol B.
Sure. Does A go first?
It could be B, not a caret.
Right? Because they're saying there is injustice, so B goes first. I will protest is the second part, and yes, since and is the connecting word, right? That's the caret. All right, part B, if there is injustice, then I will protest. If there is injustice, then I will protest. What will this look like in symbols?
Arrow.
Yeah, one direction, right? So again, there is injustice is going first, so that's the B. I will protest is the second part, and since this is an if-then statement, it's an implication or conditional. You're of course going from the direction of E to, oh my God. You're going from the direction of if to the direction of then, right? So it's if, then. Part C, I will protest if there is injustice. I want you to think about this guy because they're changing it in English, right? But symbolically, what would this look like? I will protest if there is injustice. Oh. So what's the premise here, the initial part, the if, then part? Not a carrot.
And
Would it just be a backwards arrow?
I guess what would you call it?
So if
No,
it's
arrow's
a-
gotta be going from left to right, so you don't wanna really change the direction of the arrow. Go ahead, Anna, you were saying something.
So whatever the little,
So that carrot only represents and, I'm not seeing an and in this
Oh.
statement here.
Isn't it just the same as the other one? It's technically saying the same thing.
Yes, it is. It's just rewritten in English differently. You will still see with the if, there is injustice part, right? So that is still the if there is injustice, so that is still going to be B. Even though you're not seeing the word then, you are saying, we're basically saying, if there is injustice, then I will protest. They're just not using the word then and they've moved it to the front. But the symbolic translation, yes, B and C are exactly the same. They're just written differently in English. And this is why math is so much easier than English. There's only one way of writing it out. Even if you have multiple different, no, honestly, because in English, we can rephrase, right? But symbolically, they're all going to mean the same thing. All right, part D, if there is not injustice, then I will not protest. Look at that, perfect, because there's negations on both, right? If it is saying there is not injustice, so that's a negation on B. I will not protest, so there's a negation on A, and then following that same if then, right? The injustice is still the premise, the protest is still the conclusion. Very nice. All right, you're on your own, number 4. So this time they're saying A represents it's time to eat, B, I am hungry. But we are at lunchtime, aren't we? Close to it. A represents it's time to eat, B represents I am hungry, and then you've got those 4 sentences to convert to symbols. So let's take a look at what you guys found. Interestingly enough, they have not used or anywhere in this, have they? It's time to eat, and I'm not hungry, it's not time to eat. It's time to eat, then I'm hungry. If I'm not hungry, then it's not time to eat. Apparently, they left the or part out, but forgot the others. Time to eat is A. Not hungry is negation on B, and what's the symbol?
I don't know what it's called.
Give me a shape. Second A without the bar,
Oh, yeah.
or it's technically, yes, it's called a carrot. K-A-R-A-T, carrot? I think. Alrighty, very good. So you can see we had it's time to eat, which is exactly the same as part A, or what we're defining as A, but you did have I am not hungry, so that's where the negation comes in. And then they're using and to connect the 2 propositions. Perfect. Part B, it's not time to eat. Very good. Negation. If it's time to eat, then I'm hungry. you can be hungry without being time to eat though. Anyway, if it's time to eat, then I'm hungry. A-L-B, it's time to eat. Very nice, I am hungry. All right, very good. Last one, if I am not hungry, then it's not time to eat. Now it's making me hungry. Yeah, not the right time. We should have done this at the beginning of class instead of the end, but okay.
That would have been worse.
That would have been worse, okay. So it's if I'm not hungry, then it's not time to eat. Symbols. Very good. So this time we're saying not B is the premise, then it's not A. Yeah. Alrighty. Anybody have questions on just converting words to symbols? All right, let's save this guy. Maybe got him there. All right, just very quickly, guys, here, we have about a minute. So remember, the and the or, the truth values are still gonna be the same, right? But we can define what A or B statements can be. So here they're saying, let A represent, I live in Oregon, let B represent, I go to Portland Community College, but it's still gonna be the same thing. If you have, you can see they've already filled in the first part. So this can be true, false, true, false, and you will see it follows the same pattern, right? We have two T's, two F's, and then the T and the F alternate for the second one. And you can see the only time an and is going to be true is when part A and B are true. With all the other, as long as there is one F, it's gonna be false, right? So that's not gonna change, even if you bring in what A and B represent. If you look at A being I'm a psychology major, B says I am planning to transfer to Portland State. Same thing, alternate those B values. And then remember, the only time an or statement fails is when both of them are false, right? In all the other cases, it's gonna be true. But you can see what happens when they bring in A and B sentences, and then you can see if this was true for me, which condition I would fall under, right? Am I living in Oregon and going to Portland Community College? Then you are in the two truths. Am I a psychology major and am I planning to transfer to Portland State? You can say no for both of them, and that means none of those is gonna happen. So it's for false statement for our situation, right? So you can kind of see how then that would apply once you bring statements in. So we'll actually continue with this because I do want to give you guys a chance to practice more with truth tables before I send you out into the wild on your own. So I do promise I will open that homework before you see me on. Perfect. Thank you very much. All right, guys, go eat. Don't be hungry. Have a great afternoon, and I will see you on Thursday morning.
Honestly.
Whatever.